We're going to be working on an ALEKS problem dealing with solving for a gaseous reactant using gas laws. In this particular problem is dealing with combustion of hexane to produce something called a greenhouse gas. And greenhouse gases are just gases in the Earth's atmosphere that trap heat. So this has two questions. The first one is to write a balanced chemical equation, including physical state symbols for the combustion of liquid hexane into gaseous carbon dioxide and gaseous water. So we're going to start this off with liquid hexane. And we know that this is a combustion reaction, so we have to include oxygen. And this yields gaseous carbon dioxide and gaseous water. So we've got our reactants, we've got our products, and we've got our physical state symbols. Now we have to balance this equation. And there's a few ways of balancing this equation. I like to balance all of my elements and leave my diatomic oxygen to the very end. So I have 6 carbons on the left, so I need 6 on the right. I have 14 hydrogens on the left, so if I put a 7 there, I get 14 hydrogens. Now what's left over is just the oxygens. On the right, I have 12 oxygens from the carbon dioxide plus 7 oxygens from the water. So 12 plus 7 is 19. I have 2 oxygens on the left, so I'm going to use a fraction. 19 over 2 times 2 is 19. So I can keep it this way to start me off, but my final balanced chemical equation needs to have whole number coefficients. So in order for me to get rid of that fraction, I'm going to have to multiply the entire chemical equation by 2. So I'm going to distribute the 2 to every molecule in this chemical equation. So this gives me 2 C6H14 and 2 times 19 over 2. So this is like saying 19 over 2 times 2 is just 19. So now I have 19 oxygens. 2 times 6 is 12. And 2 times 7 is 14. Let's see if we did this right. I've got 12 carbons on the left, 12 carbons on the right. I've got 28 hydrogens on the left. I've got 28 hydrogens on the right. I have 38 oxygens on the left. I have 24 oxygens from carbon dioxide, 14 oxygens from the water, so that is 38 oxygens. So this is my balanced chemical equation with the physical state symbols. Question 2 says, suppose 0.2 kilograms of hexane are burned in air at a pressure of exactly 1 atmosphere and a temperature of 19 degrees Celsius. Calculate the volume of carbon dioxide gas that is produced, and be sure your answer has the correct number of significant digits. So this is my balanced equation. I'm going to go ahead and write down my given information. They give me the pressure. They give me the temperature. I can go ahead and record my R. I'm using the table from ALEKS. And they're asking me for the volume of carbon dioxide. So I want to make sure I remember that they're asking for the volume of carbon dioxide. But what they did give me was the kilograms of C6H4. In order for me to use the ideal gas law, PV equals nRT, I need the N of CO2 before I figure out the volume. I can go ahead and do a conversion of 0.2 kilograms of C6H14 to moles of CO2. So I'm going to give myself a roadmap, make sure I know what I'm talking about. I'm starting from kilograms of hexane, and I'm going to moles of CO2. Always start off with my given information. Kilograms of C6H14 is on top, so I have to put kilograms of C6H14 on the bottom. 1 kilogram is equal to 10 to the third grams. So now my kilograms cancel out. Go ahead and put grams on the bottom on my next fraction. Remember, I'm trying to go from hexane to moles of CO2. So I'm going to go ahead and convert my grams to moles by using the periodic table that's in ALEKS. So 86.1674 grams of C6H14 is equal to 1 mole of C6H14. Moles of C6H14 on the bottom. I want to now do a mole to mole ratio so I can go from one formula to another. I take a look at my balanced chemical equation. For every 2 moles of C6H14, there are 12 moles of CO2. And this all equals to 13.926 moles of CO2. Now I have enough information to use the ideal gas law, PV equals nRT. Now, before I use this formula, I need to make sure all of my units are in the correct units. My temperature is in Celsius. I'm going to go ahead and convert that to Kelvin so that all of my units can cancel out. Now I can go ahead and plug these numbers in. I don't know what volume is. I do have now the moles of CO2. I have my R. I have my temperature. Go ahead and solve for V. Okay, and I get 333.85 liters. But I want to make sure that I report in the correct sig figs. I look at my given information and I have 0.200 kilograms of hexane. That's 3 sig figs. So my final answer needs to have 3 sig figs. So 334 liters is my final answer. Let's take a look at another example. In this ALEKS problem deals with the decomposition of sodium azide, which is involved in airbags. For the first part of the question, they want us to write a balanced chemical equation, including the physical state symbols for the decomposition of solid sodium azide into solid sodium and gaseous dinitrogen. So we're going to go ahead and write that down. Solid NaN3 decomposes to solid sodium and gaseous dinitrogen. And the next thing we're going to do is go ahead and balance this out. Let's make sure we did this right. 2 sodiums on the left, 2 sodiums on the right, 6 nitrogens on the left, 6 nitrogens on the right. So now we have a balanced chemical equation and we have our physical state symbols. The second part of the question says, suppose 67 liters of dinitrogen gas are produced by this reaction at a temperature of 16 degrees Celsius and a pressure of exactly 1 atmosphere. Calculate the mass of sodium azide that must have reacted and be sure your answer has the correct number of significant digits. So the next thing we want to do is go ahead and record our given information. They're telling us that we have 67 liters of dinitrogen. So 67 liters of dinitrogen. And let's go ahead and record the rest of our given. Our temperature is 16 degrees Celsius. Our pressure is 1 atmosphere. Our gas constant is given in the ALEKS table. And they're asking us for the mass of NaN3. So they've given us the volume of N2, but they're asking us for the grams of NaN3. So we can actually go from moles of N2 to grams of NaN3. We have the ideal gas law, PV equals nRT. So let's make sure all of our units are correct. Our temperature is in Celsius. So we're going to go ahead and convert that to Kelvin by adding 273.15. And now our temperature is in the correct units. Okay, so I have my P, I have my V for N2. I can solve for my N, the moles of N2. I have my gas constant and I have my temperature. So let's go ahead and plug in these numbers. And I solve for N. I make sure to write the complete units so that I don't get confused. I just solved for moles of N2. But they're asking us for the mass of NaN3. So I'm going to go ahead and make a roadmap. I'm going to go from 2.8238 moles of N2 to grams of NaN3. Always start with my given. Moles of N2 is on top, so moles of N2 go on the bottom. Take a look at my balanced chemical equation. For every 3 moles of N2, I have 2 moles of NaN3. I'm going to put that in my stoichiometry relationship. So for every 3 moles of N2, I have 2 moles of NaN3. Moles of NaN3. 1 mole of NaN3 is 65.0096 grams of NaN3. And this gives me 122.38 grams of NaN3. But I want to make sure that I'm reporting my final answer in the correct sig figs. My volume is 67.0 liters. That's what we started with. That has only 3 sig figs, so my final answer needs to only have 3 sig figs. So my final answer is 122 grams of NaN3. Good luck and keep practicing.